Hello and welcome back to Calculus 1, section 3.3, Rules of Differentiation. You simply love taking those limits, right? Right? I mean, if you're okay with taking the limits, then we're done. We can go chapter 4, right? So what is the rest of chapter 3? Rest of chapter 3 is going to be on shortcuts. So we don't have to do those limits anymore. That's what chapter 3 is all about. So we define the derivative, we understand its purpose, we understand what it is, and we know the definition through the limit. And technically, we could just call it a day. But calculating those limits tends to be very annoying, and the problems are going to get more complicated, and those limits are going to get far more complicated. So is there an easier way? I mentioned this before in class. This section is really convenience. You are going to memorize a whole bunch of derivatives so that you can skip limits. I always travel in pairs. Right. Fine. So I did talk about 3 times 5 is 15, because you don't want to go 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15, because that's annoying. Especially it's annoying when you get to, I don't know, 7 times 9 is 63. And then you go 9 plus 9 plus 9, right? It's a lot. So you sit down and you memorize 100, right, of these in multiplication tables, so that you can quickly get through that. This is exactly what we are going to do now. I'll give you the rules of differentiation, and you're going to memorize those so that you don't have to do the limit every time you need a derivative. And we are going to need a lot of derivatives. So we start with the first rule, and that first rule is that the derivative of a constant is 0. You can also read this and understand this as the change in constant is 0, because we know derivatives measure change. Constants do not change, they're constant. So there's no change in a constant, therefore derivative is 0. This is one of those formulas. And then we can just put some examples as the derivative of 3 is 0, or derivative of 2/5 is 0. Derivative of pi is 0, or pi over 2, right? So derivative of a constant is a 0, and that's that. Now we're moving to the next one, and the next one says the derivative of x to the n is n x to the n plus n minus 1. And plus 1 is for integration, and minus 1 for derivative. So n minus 1. Now, please note that this is not only taking care of x to the power of 2 or 7 or something like that. Sure. So you can take x to the 7. Yeah. But this also takes care of, let's say, a 4th root of x, and it's also taking care of 1 over x to the, let's say, 9. These are the 3 types of problems that are solved by this derivative. So we're talking about polynomial, radical, and rational functions. That's a lot. Now you have to use algebra to massage this into the x to the n. So this one will be x to the 1/4. So your n is 1/4, and then you do your calculation. Over here, algebra says that this is x to the -9, and then you can do your calculation. And obviously this one stays as x to the 7, right? So now, so I'm going to ask you to solve these three problems using the formula that you see. So what is the derivative of x to the 7? What is the derivative of 4th root of x? And finally, what is the derivative of 1 over x to the 9? Step number 1, obviously, is to rewrite the whole thing, and be very careful with your notation. There's only one way. Let me rewrite one of these for you. So you have to say, take the derivative of x to the 1/4. So now you know how to rewrite. That derivative still has to be there. Just like limit has to be in each step until you get to use it. All right, so let's take a look. Our n in the first example is 7, so we copy 7, and then x to the 6, you subtract 1. It's that simple. The limit would take like 20 minutes because you would have to have x plus h to the 7th power, and you would have to expand that, and then stuff will cancel, and then eventually you would get the same answer. So, yeah, a little bit involved, right? Next example, n is 1/4, so you copy 1/4, x to the -3/4. Good effort. You can leave it like this, or you can write this as 1 over 4 times 4th root of x cubed. You can do that as well. That's just, showing some algebra muscle right there. And finally, The one on the bottom we are going to rewrite as x to the negative 9. So negative 9 drops. We have x to the negative 10, because negative 9 minus 1 is negative 10. And that will give me negative 9 over x to the 10. One example that we dealt with before was using the limit was the derivative of 1 over x. This is something that you want to memorize, this 1 over x, because it shows up a lot. So this is the derivative in respect to x of x to the minus 1. So you drop negative 1 times x to the negative 2, which is negative 1 over x squared, as we have seen in our calculation with the limit. This is much shorter, right, than doing the limit. So I would say you should memorize these rules. So we already covered a lot. Two formulas, but these two formulas, as you can see, cover a lot. So now I need some rules to attack more complex problems. For instance, if I have, we can't do this yet because I need to write the rules, but if I consider the derivative of 3x squared plus 6x plus 9, let's say, or no 9, let's go with 5. So if you are considering the derivative of this, you see that you don't have just what you are used to, basic functions and constants. You have them added, and you also have 3 and 6 as coefficients. So we need the rules that deal with that. And those rules are the derivative of f plus g is the derivative of f plus the derivative of g. Now this tells us that we can take the derivative of each one of these separately. We don't have to regard this as a one quadratic function. We actually regard this as 3 functions: quadratic, linear, and constant, and take derivatives of each term independently. The companion formula here is going to be, if you have a minus, you will just have a minus. So I just added minus under these pluses, and there you go, 2-in-1 formula, okay? And now what happens with a constant? If I have some kind of number multiplying the function, that number can be kicked out in front of the derivative. And then you just focus on the derivative of the function. These rules are known as rules of linearity. These rules existed for your limits. These rules exist for derivatives, and they will exist for your integration eventually. A linearity rule. And it's going to be everywhere later on in...
So the same properties that we use to compute functions are all applicable to derivatives as well?
Yes. So now, to go back to the problem, I can break this problem down into the derivative of 3x squared plus the derivative of 6x plus the derivative of 5, and then using the second rule, kick 3 outside, and then I'm just focusing on derivative of x squared, plus kick 6 outside, focus on the derivative of x, and then you just have the derivative of a constant here. So now This is going to be 3 times 2x plus 6 times 1 plus 0. So the total derivative here is 6x plus 6. Now, within a week, you will go immediately from the problem to 6x plus 6 immediately. Because you will say, oh, 3 times 2 is 6, and then x goes away, and 5 is 0. Right? So this should be, on the first homework, you will be done with that. You will never write all these steps because they are completely unnecessary. But in this case, right, they illustrate what's happening. So let me talk more about that shortcut. So if you're having the derivative of 3x squared, I already told you the way to do this is to just say 3 times 2x is 6x. Because we copy, right? We copy constants. That is, in this rule, the constants gets just copied outside. So this is our basic rule. Now, some of you might be wondering why is the derivative of x1? Well, I would like you to discover that now. What is the exponent on this x? 1. Thank you. So run the formula knowing that the exponent is 1. I kind of added, I wrote 1 this way because I don't want this to be confused with x prime, right? So it's x to the first power, so x to the 1, not x prime. So, what happened?
Connect to the 0.
Very good, yes. So you drop 1 down, and then you have 1 minus 1 is 0, x to the 0 is 1, 1 times 1 is 1. Good. So you drop 1 down times x to the 0, which is 1 times 1, which is 1. This is why every time you have a linear function, it will go down to 0. Down to constant. Constant will go down to 0 as you progress. We have 5 rules so far. The derivative of constant is 0. The polynomial rule, which also takes care of rational and radical functions. And then we have the linearity, 3 rules of linearity, addition and subtraction. They can all be done term-wise. And then the constants get kicked out, and you just focus on a function. All of these rules in our honors Calculus 1, students are responsible to know the proofs, the limit proofs for each one of these, and then so each one of these rules that I'm writing now, they have a full limit proof that you can do and prove the rule, because these are shortcuts, right? And once you prove the rule, prove the shortcut, then you can always use it. Now, in non-honors courses, we skip over that. We just say these are the rules, memorize the rules, right? You don't have to prove the rules. Everyone, honors Calculus 1 still has to memorize the rules. Just in addition, they also need to know how to derive those rules. You definitely want to memorize them because you don't want to sit there and crank the limit to prove the rule and then use the rule, right? That beats the purpose of everything. The idea is to eliminate limit completely from our calculation until we hit chapter 5 and see the integral definition, definite integral. So we have all of those, and The last rule, the function here, is going to be the exponential function e to the x. The others will be taken care of later. So if you want to take derivative of, let's say, 2 to the x or 5 to the x, that's later. We are now focusing only on e to the x. So the derivative, does anyone know it, of e to the x is e to the x. This is the only function that does this. The derivative is equal to its function. Now, this is the form that you will rarely use because we generally want to see e to the 3x, e to the 2x, right? And they ask you to memorize now, even though we're going to have a tool later to deal with this. So e to the ax is a e to the ax. So it's technically this formula that it's going to be used most of the time to calculate derivatives. So example would be e to the 6x. Well, it's terrible. So the derivative in respect to x of e to the 6x is 6 e to the 6x. That's the example. Yes?
Are you actually able to take derivatives of inequalities?
You are taking, well, it's not really related to this at all. Because you are not taking the derivative of equation. You are taking the derivative of expression. E to the x is not equation. E to the x is just a function. When you say e to the x is equal to 7, then it's equation. And you can calculate for x. See, I am looking for the derivative of x squared plus 3. X squared plus 3 is not an equation or an inequality. It's just an expression. The answer is 2x, right? Now, if I say 2x plus 3 equals to 0, it becomes, in that case, it becomes equation or inequality. But we don't have any of that stuff. We just say, take the derivative of that. And this is the instruction, just like license and registration, right? That's the instruction on what to do. Just like your limit, you take the limit of 2x plus h as h goes to 0. This is the instruction what to do. Limit, take the limit as h goes to 0 means kill 0, answer is 2x, right? So you have the instruction piece, then you have the function, then you have the answer. You have the instruction piece, then you have the function, then you have the answer. For integration, it's going to be the same thing. You have the instruction, then you have the function, and then you have the answer. So, again, instruction, function, answer. They're all the same in terms of the way they are laid out for you to do the work. The limit, derivative, integral. 3 pillars of calculus. You will say limit of a function, derivative of a function, and finally integral of a function. So you need to know that the expression you have is a function. Bueno? Good. All of this is now gone, and I'm going to put an example for you to enjoy. So, let's first do this example. So, derivative in respect to x of 10 over e to the 6x. Well, how would you do this problem? So the first thing I'm going to do is rewrite this. The derivative of 10 times e to the negative 6x. We know we are supposed to copy the constant, which is 10, and then the derivative of this is negative 6 e to the negative 6x, for a total of negative 60 divided by e to the negative 6x. Positive 6, sorry, positive. That's why we put that in denominator, so we don't have negative exponent. So rewrite, and then we do the derivative using the rule. The rule says you have your a, which in our case is negative 6. You drop that negative 6 in front, and then you copy. Control C, Control V, right? So you copy the same thing. So that's exactly what I did. As you can see, ignore 10 because that's the constant you rewrite. You drop down A, and copy the rest, and then you put that in the denominator. Good. All right. So here is the example for you. One more. So we have 3x to the 4th minus, let's go with 10, x to the 5 minus the square root of x plus e to the 4x. This pretty much covers everything we did. Would anyone like to do this on the board? Explain to everyone? Yes, it's going to be communications, right? Yeah, the markers over there. I think this one is the best. We'll do it here so we don't have to erase the screen. What we're going to do for notation. Nothing is labeled. There's a lot of stuff missing. That's okay. All right, I'll add the stuff that's missing. Problem is correct. It's just that a lot of stuff notationally is missing, which clearly deducts from everything. So if you are not going to use the notation with take the derivative of, you will have to write that this is the function. So f of x has to be here, say equal, and because that's f of x, then these guys are f prime of x. And this is also f prime of x. So this is the part in the notation that must be present. Actually, sorry, this is not. This is also a function. Rewrite. Another thing is that this x needs to go up to the 4. So this x where it belongs. And that's it. So we have 3x to the 4, perfect, negative 10x to the minus 5, perfect, x to the 1/2, perfect, and this stays the same. The derivative here, 4 times 3 is 12, x to the 4 minus 1 is 3, perfect. Negative 10 times negative 5 is positive 50, and then it should be x to the minus 6, so over x to the 6, good. Over here we have, well, this is one of the ones that might be harder to see. We have the derivative of x to the 1/2, right? So that's going to be 1/2 x to the negative 1/2, because 1/2 minus 1, right? 1/2 minus 1 is negative 1/2. So negative 1/2 is the square root of x in denominator. So that's why I have it there. And oh, there's a 2 missing. There's a 2 missing right there. And then you have a 4e to the 4x. For the first attempt, this is perfect. I mean, but the notation has to be followed for the I don't want to say full credit. I don't care about the credit, but you might care about the credit. So I'm going to rewrite this as take the derivative of 3x to the 4th minus 10 times x to the negative 5 minus x to the 1/2 plus e to the 4x. And then we have the derivative of 12x cubed plus 50x to the negative 6 minus 1/2 x to the negative 1/2 plus 4e, wow, not derivative there, 4e to the 4x, because I'm taking the derivative. So the lines where you have the function will have still the instruction take the derivative. Once you take the derivative, you used it up and you don't have to write it again. So now we just rewrite the answer. 12x cubed plus 50 over x to the 6 minus 1 over 2 square root of x plus 4e to the 4x. And this covers all of the rules we did. I didn't have the constant. I could have put like plus 10 at the end or something, and or plus 5, whatever. But this is good enough. The last part of this lecture is going to be higher order derivatives. Higher order derivatives. We said that the derivative is a function, which means that once you find the derivative, and derivative is a function, you can take another derivative of that function to come up with another function. And then you can take the derivative of that function, and you can chain this as far as you want. Let me give you an example of our good old friend from a few classes ago, saying f of x, or f of x is equal to 3x squared plus 1. I think this was one of the functions we used. So the first derivative is what? What? 6x, very good. So you notice that I labeled first derivative is. This is extremely important, because now the next one is the second derivative. And what's the answer there? 6, very good. And then I have a third derivative. What's the answer there? 0. So you keep taking the derivative of the last line you have. Now, the fourth derivative switches the notation. You see that we have now we start with numbers in parentheses. And I hope that you realize now that every next derivative you take is going to be 0. Right? Because the derivative of 0 will always be 0 as you go on. Please don't draw any conclusions from this example in terms of, oh, as I take many derivatives, derivatives go to 0. That's not true. Only polynomials do that. Let me ask you, if I give you that f of x is equal to e to the x, and I ask you what is the 107th derivative of e to the x, it's still e to the x, right? So see, if you go and sit and actually take 107 derivatives, every time will be e to the x, e to the x, e to the x, e to the x without a fail, right? Or what if I say the function f of x is equal to e to the 2x? What is in this case 107th derivative of x? What do we want to do with this 2? What happens with it? Yeah, it goes in front. So it'll be 2 to some exponent e to the 2x, right? Now let's think about it. F prime is going to be 2e to the 2x. F double prime is going to be 2 times 2e to the 2x, because this is copying the previous function and then dropping another 2 from the exponent, right? And then the triple derivative here will drop yet another 2 e to the 2x. So what is the exponent that goes here? It's 107. First derivative, 1, 2. Second derivative, 2 2's. Third derivative, 3 2's. 107 derivatives, 107 2's on a pile as the exponential. So 2 to the 107 times e to the 2x. So there are no shortcuts here, unfortunately. If I need the fifth derivative, you have to compute first and second and third and fourth, and then you get to the fifth. So now, for our application, we generally only take 2 derivatives, second derivative, sometimes third. We are going to have next class full lecture on that velocity and so on. You will have, and the book gives you first and second derivative, which is velocity and acceleration. There is one more topic that you cover in physics class called jerk. Jerk is how fast you slam your gas pedal or step on your gas pedal or your brake. You experience jerk. Jerk is the change of acceleration, right? And you can press your gas pedal slowly, right? And you are not experiencing jerk because you're just, right? It's a gradual change. Or you slam on the brakes because there is something in front of you, right? And then you hit your face in the steering wheel, right? That's a jerk. That's what's happening there. Which is why you have a seat belt on, so that when you slam on the brakes, the seat belt is not getting you to smash your face into the steering wheel or fly out through the window. The little headrest or whatever it's called on the back of your seat, if you get rear-ended, thank you, rear-ended at the light or a stop sign, right? That is actually giving a lot of acceleration to your car forward, right? Because you're getting hit. You see, this is your car, and you get hit and you go forward. Well, it does that to your neck, jerks it back. That's why you have that thing in the back, which you should always extend. Right? Sometimes when people are larger in smaller cars, they don't actually extend it, so they still get the neck injury if they get hit in the back. Right? That needs to be positioned to hit right here, and it needs to be firm. Otherwise, it's a trouble if you get hit. And you don't get to control that. It's just your lottery ticket if you're going to get rear-ended or not. Right? You worry what's in front of you. You can't worry what's behind you. Right? So, that is the third derivative. Fourth derivative, I only see it once for application in a graduate program, okay? So, you worry about first, second, and third derivative, and the fourth one is going to be extremely rare. Now, can I ask about 107th derivative? Sure, we call that mathematical gymnastics, right? You can have any derivative you want. It's just how much I want to annoy you, right? With a question. Find the 7th derivative, right? Then you have to go home the first and the second and the third and the fourth, right? So that's that part. It's not hard, it's annoying. That there's a difference between the two concepts. So those are the higher order derivatives. Please remember that the higher derivative is always the first derivative of the previous one, right? So what is the sixth derivative? Sixth derivative is the first derivative of the fifth derivative function, right? Because you always take the first derivative moving on. This was the good example, right? To get to the third derivative, you take the first derivative of the second derivative. That's the meaning of this, and you also have to take all of those. You can't skip any of those. And that's the higher order derivatives. And then you have a whole bunch of homework to do. So we'll take a break. Bye.